Swayam Prabha. Digital India. Educated India.
Section lecture is review of vibration system and understand you have different background. Therefore, some natural or not equations I may skip. Okay, so but I will send you guys the PowerPoint, the slides anyway. Okay, so this is outline. Okay, single D freedom vibration system and free vibration, forced vibration, and power and energy in the vibration system. And the last section I may skip and the impulse response. Okay, so we already get a sense that this is a vibration system, right? Wave energy converter. And the vibration system why I cannot stop that? Okay, so here you get a sense about vibration system, right? So you have vibration amplitude and this period. This is a very important concept. Okay, and there are different type of vibration system. One is free vibration, forced vibration, and damped vibration. You can get a sense like free vibration system, right? Like that. You pull this spring and release that is free vibration. It will continue to vibrate, right? Force vibration is you have force, you act on that, and you have harmonic force is always like that. This is force vibration, right? And then damped vibration, and damped vibration, in addition to the spring mass, you have a damper, right? Dissipate energy. The vibration happen here quickly reduced. This is damped vibration. So for spring mass system like this, and you can draw the free body diagram, right? Here you have positive direction like this, then you have force is kx. Now using Newton's law, you write an equation, right? And so Newton's law, you write a equation of motion, right? And now you normalize in that way, divided by m. So then you define square root k divided by m as natural frequency. The equation can be written in that way. So, and how to solve this equation, right? And the solution will depend on the initial condition. Here, initial condition means time at 0, what the displacement, what the velocity. So, and you assume the solution is harmonic, right? And the vibration frequency same as the natural frequency I and B. And B are the constants that depend on the initial condition. You plus x t equals 0, right? And this item disappear. You get A equal x 0 dot, right? Then you solve for B. Eventually, you get the vibration equation like that. So this system, there's no damping, right? Undamped vibration system. And the combination A and B, this amplitude, you can have amplitude and phase, right? You using triangular relationship. So this overall, the solution is like that way. So here, the triangular relationship shows the A amplitude, which is cosine amplitude, and B sine amplitude that depend on the initial condition of displacement and velocity, right? You can write the amplitude that is C, right? This is phase, right? So this is single D freedom vibration system. So amplitude and phase. And that is time domain, what's look like that? Okay, so if we look at this system like this, time domain, this system vibrate harmonic, always periodic, right? So this period, and is 2 pi divided by omega n, natural frequency. Here from this, you have initial displacement then the velocity is the slope dx dt, right? This velocity slope. So in this figure, you can have period, amplitude, initial condition. So, and also you can get the amplitude c and phase. Okay. So another thing is called this time domain. Another is phase plane. Phase plane, you have displacement, you have velocity, right? You plot this one, and look like you have elliptical, right? And you normalize and x by amplitude, phase the velocity by c times omega n. So overall will look like a circle. Okay, so this is phase plane. Phase plane sometimes is more convenient than the time domain vibration. Time domain you can understand very easily, and phase domain sometimes we use. You have damped vibration system, you can say this system vibrate, become smaller, smaller eventually to the center. Okay, so this is phase plane, this is vibration. Okay. So this is free vibration. Another says damped vibration. Damped vibration, you have damping. Therefore, the vibration system, when you draw the free body diagram, you have c times x dot, right? Xc is constant. This is damping coefficient. X dot is velocity. We assume that's linear damping, very popular damping assumption, right? So basically the damping force is proportional to the displacement. So then you solve this problem, you assume that A, E, lambda T, right? In that way, you get a characteristic equation. You plug this into this equation, then this lambda. When you solve this lambda, this is second order constant coefficient equation, right? So ODE, right? So then you have lambda equal this form, right? So you can say this c square minus 4km. This item is important. This item can be positive, this item can be negative, this item can be 0, right? When this item to be 0, we call the critical damping, right? So these critical damping coefficients make this part to be 0. In that way, you have repeat eigenvalue, right? So this is we call C that make this item to be 0 will be critical damping. The damping ratio is C divided by this critical damping. Okay. So, and depend on the damping ratio, right? We have lambda 1, lambda 2 in this way, and zeta here it can be greater than 1 or negative than 1. If for greater than 1 case, and this is called over damped case, and less than 1 case is called under damped case. Then zeta equal 1, this is critical damping system. So for vibration system, you look like a time domain like that, and if you have under damped cases, blue color, you have vibration, right? And for over damped case, this case, there's no vibration, it's just decay, right? So real line shows a critical damped case. Critical damped case usually you get to 0 faster than any part, other part. Okay, so and this phase diagram, as I mentioned to you, right? If damped case, this can gradually like go to smaller to the 0. So for vibration system, especially for ocean wave, and mostly is under damped case, there's a vibration. So okay, so now if we have more interest to the under damped case, so here and we have natural frequency, we have damped natural frequency. Damped natural frequency is omega times square root of 1 minus zeta, right? If we have damped natural frequency, after define, you can write the lambda 1, lambda 2, the eigenvalue in this way. Now you have lambda 1, lambda 2, so the solution you combine them together, right? A1 e lambda 1t plus I2 e lambda 2t. So in such kind of system, you can say the expression we can write in that way. Okay, I go this very quick. Okay, so if you cannot find write down the notes, it's fine. I'm going to email you guys the the PowerPoint file. Okay, the file is large. I'm going to use convert into PDF. Okay, so this part is important, and right, for this part, what's this part? This part ej omega ej omega d times t, right? So this omega d times t look like phase, right? And this point is in rotation, j omega, okay. And with the time going on, this angle will increase, right? This Euler formula, this EJ file will be real part, the projection, this real part, and the imaginary part. That is the circle is unit, right? So using Euler formula, we can write E j omega t with cosine j omega t plus I j, or sometimes we use I, some j, same. Okay, so omega t. In that way, we can combine the certain solution. Okay, and here I1, I2 will depend on the initial condition. So after that, you using Euler formula, you plus the initial condition, you get the solution here. There are two parts. One part is this one, and this part, with the time going on, it becomes smaller and smaller, right? And this part will never become smaller. It's a harmonic term, right? This all oscillation due to initial disturbance. That's the exponential decay. In time domain, what's look like that? I just copy and paste this here. Okay, and this is also amplitude. Okay, C and 5, and so this is the important figure. Okay, this figure shows the free decay result, and free decay, and you can free decay is based on such kind of initial condition, right? In this one, you can say several sense. One is initial condition, right? And initial condition amplitude, sure, there's a slope, there be the velocity, right? Another thing is the free decay, and if you draw the envelope here, and then you can calculate the damping coefficients from how fast it decay. And the third part is the damped natural frequency. Damped natural frequency, you can say, you can measure from 0 to 0, and you can measure from here to here, right? So anyway, and the damped natural frequency. So this figure, sometime when we use for the tank, a wave tank test, and you give the initial position of the buoy, and that is the free decay. Then from free decay, you can calculate damping, right? You can get natural frequency. You can recover stiffness. That is the experiment I believe Dr. Vijay will show you about in the tank test. So, and later I will tell you this free decay sometimes we call the impulse response. Free decay, impulse response different, right? Free decay usually is a response to initial condition. The impulse response means you give impulse. You will be confused, and you can tell me why. I will explain to you why they are the same. Okay. When we learn the wave dynamics, okay, you will find free decay and impulse response means same. Okay, free decay, that is, you give initial displacement. Impulse response, you give the impulse of velocity. Impulse velocity will be same as the initial position of the displacement. Okay. So anyway, we look into force vibration, right? Force vibration, you get force, you draw free body diagram here. After the free body diagram, and you write the equation like that, and you normalize in that way by divide by mass. Okay, so how to solve this problem? There are two parts. One is homogeneous part and non-homogeneous part. Okay, so the solution. Okay, so the solution, there's a general solution and particular solution. General solution will be same as the initial condition. Eventually, it will die out, right? Because this term, okay. And particular solution will not die out. So particular solution, there are two terms, and is amplitude and frequency. And this general solution, the frequency is damped natural frequency vibration, right? And particular solution, the solution is the excitation frequency, are different. So, and then you can solve this general solution, right? If you have harmonic Fe, this amplitude excitation, and you can plug this equation to this here. Okay, you can find amplitude and phase relationship. I didn't go through the detail, so this is called amplitude response and phase response. So then that is normalized amplitude, right? So this amplitude, this Km, right? And if you normalize this natural frequency and damping ratio, you can write it in that way. So these two will be the same. So this normalized natural frequency, the normalized amplitude and phase. So, and I already told you this complex sinusoid, and just now this real sinusoid. To solve this problem is a little bit complicated. You plug that in, you need to solve this triangular relationship. Or another way, if you use complex excitation here, and like this one complex excitation instead of sinusoid, and this everything equation will be much straightforward to solve this problem, right? And here the x is complex number, ej omega d, omega, you have instead of sine term or cosine term, use a complex amplitude. So from this complex amplitude, you can directly solve this complex amplitude x, right? And plug that into here, you can get this equation, e j omega t, j omega cancelled. You can directly solve that's x. Okay, this is complex response. This you say this real part, this there's an imaginary part, right? So here you can write this amplitude and phase. Amplitude and phase is same as the result we got from previously when we have real excitation sine and cosine term. Okay, understand that is probably too much for the sophomore students. However, I want to put one figure in your mind. Okay, this figure. So this figure is amplitude, right? And you understand the resonance, right? If vibration at the natural frequency or around the natural frequency, amplitude is very, very large. Okay, and if in this figure you also get a sense. Now, when we increase the damping, the amplitude becomes smaller and smaller, right? This resonance. So another thing is when the frequency is zero, what's the meaning of vibration frequency zero? you have constant. You just pull the spring, right? This frequency 0. So if we have frequency 0 and the vibration amplitude will be static deformation, right? The damping doesn't matter, only spring matters, right? You have constant force, only spring matters. So that is called stiffness dominate, right? Another thing is very, very high frequency. If we have high frequency infinity, which one matters? You look at, you have multiple ways to look into that, and once from this response, and R is normalized frequency. If frequency is infinity, and this is power 4, right? This is power 2. Therefore, damping wouldn't matter. So only in that frequency, everything go to one line. It doesn't matter. That kind of thing is mass dominate. You see this here, and if omega go to 0, this term is omega power 2. This term omega power 4. And omega power 4, the coefficient is m. Therefore, mass matters. So around this thing, damping matters, around the resonance, right? And in particularly is R equals 0, Y equals 1. That means omega excitation same as natural frequency. This time stiffness and mass cancelled. When stiffness and mass cancelled, R equals 1, that is amplitude is 1 over 2 zeta. So we call this is quantity factor, right? This is vibration system at the R equals 1. So we say damping matters around this resonance. At this resonance, the stiffness and mass cancelled, the item disappear. So this is vibration, okay. And so again, there are not equations. I want to put this picture in your mind only, okay, especially for the student in the second year, you know, at different frequencies, stiffness dominate and mass dominate, damping dominate, right? So another thing is I skip the basic excitation, okay. So let me skip the basic excitation. I skip all this type of mathematical equation, but I still like this picture, okay. And nice view. Okay, this picture and what that mean? Okay, just I put here this here quickly. This car suspension, right? You drive the car on the road, right? This car move up and down, the car body moving, right? At a very low frequency, right? Then this car body follow the ground roughly its motion, right? This now, do you think stiffness will change everything? It's different. It doesn't matter what kind of stiffness that, and they just follow the ground motion, right? And also high frequency are different. High frequency, why is high frequency different? You look at this one. If you have small damping, the amplitude will be lower. And you have high frequency, you have larger damping, the vibration will be larger. The reason is, in the car suspension like that, the larger frequency, then the shock transmit from ground to the car body at high frequency. So therefore, you have more damping, then the amplitude at high frequency is worse. This is why, for the force excitation, what means you give the force, you want to have more damping. But for the basic excitation like car suspension, you don't have large shock absorber. If shock absorber is too large, the vibration at high frequency become bad, and low resonance become better. So the car suspension usually you have 20 to 40 damping ratio. It's just trade-off between low frequency and high frequency, right? You have damping, you reduce the resonance, but you transmit the shock to high frequency. So this is the important part, and this course we harvest energy, right? We harvest energy from ocean. You ask, where's the energy from? Okay, where's the energy from? Let us say this system, and you have vibration system, you give excitation force to that. This system is going to vibrate, right? And you write the equation m double dot plus cx dot plus kx equal f. There's no question on that. So now you want to say the power. Force time velocity will be power. Therefore, I time omega velocity to the system, force time x. That's the input power, right? Instant power. Okay, and there are terms kx x dot and mx double dot times x. Okay, and these two you can write k. For example, kx double dot is d dt times 1 over kx squared, right? And mx double dot times x dot you can write d dt 1 over 2 mx dot. So basically, that part is time derivative of kinetic energy. This part is time derivative of potential energy. That means the system, the input to the system, the input power, there are two parts. One is the potential energy and the kinetic energy change, T plus U. Another is damping term energy. So this is power dissipation from the point of from viscous damper. Therefore, you think that way. In the spring mass system, the spring store the kinetic energy, right? After one cycle, the kinetic energy return to the system. Oh, sorry, the spring store the potential energy. You pour that, this potential energy. You go through one cycle, the energy go back, right? The mass store kinetic energy 1 over m velocity square. When you go one cycle, the kinetic energy go back. How about the damping? You have spring mass damper, you go through one cycle, where the energy go? Right? The energy dissipated. Therefore, the energy harvesting itself. What you care is the energy on the damper. Is this clear? Right? So, because spring will not take energy away, the mass will not take energy away, only the damper take energy away. Right? So, this is how energy harvesting work. And you design energy transducer or PTO to take energy out. That is damping, right? So, no matter the car shock absorber like that or PTO side, this is damping. So, energy dissipated through the damping. If you give harmonic excitation, okay, and you give harmonic excitation, right? So then the damping force equals C times x dot, right? If x equal harmonic, you have frequency, you have amplitude x, you have phase. And you plug this into equation here, right? Then you draw force displacement relationship is something like loop. force displacement loop. Okay, if you hold spring, what kind of thing it look like? Force displacement is just one line, right? You just, if you have spring, the force displaces one line, right? And that means you get energy stored and get energy back. Now, for this damper system, you go through one cycle, the area under that, that's the energy. So you integrate the loop under the area, this energy, this force, time displacement, the integration. This area, that's the energy. This energy in one cycle is proportional to the damping constant, right? Is proportional to the omega, is proportional to the x squared, right? If you drive the system at large amplitude, you double the amplitude, it's like 4 times more power through the cycle, right? And you increase the damping, you get more from the system. So, look like, oh, we need a larger damping coefficient. We can get more power. Is that true? No? Why? Let me ask a second year student. Okay, look like this equation, right? We want to take more energy out. We get larger C. Larger C means larger damper. Is it true or not? Not true. The reason vibration, you have larger damper, then vibration amplitude becomes smaller, right? It's trade-off. Okay, so anyway, so the energy, total energy can be harvested is related with damper C. Okay, then damping is very important. It doesn't mean we increase damping, we have more power because the amplitude decrease. I want to have one homework problem. So, and you will find the so-called matching, impedance matching. You match his excitation frequency. You want to design the damping C to match the electric damping to match the mechanical damping. You will ask, man, what's the mechanical damping? What's the electric damping? Okay, mechanical damping means the viscous damping, the friction, all the type of thing. What's electric damping? Okay, electric damping, this you take energy out, you create some damping. Okay, I will explain to you what's electric damping. Okay, so now let us say you take energy out. This buoy system, you put a spring mass damper here. Actually, you introduce certain voice coil magnets, right? You have magnetic field. The magnetic field move inside this is coil. Then you introduce damping. So this is direct electromagnetic transducer. Okay, how it works? You learned from high school physics, right? You have magnetic field, you have conductor more inside that, you generate voltage. That voltage is B Tesla, right? And L, the conductor length, time velocity, right? That is B L velocity, right? And we write K E time velocity. This K is speed constant, right? It generates voltage. This is called back electromotive force. It's really not really force. Is a voltage. Sometimes we call the back EMF voltage. So that is proportional to the velocity. So now you short that with the electric load. You add a resistor here, right? And you have a current go through the system. So when you have current go through the system, what will have? You generate a force. This is Lorentz force. The force is BL times I, right? You learned from physics class, right? And the force is B magnetic intensity copper length time current. So Kf is the force constant, right? And you can see happen in this case Kf and Ke, speed constant, force constant same. Okay, so now the vibration system you can write in that way. This mass, this spring, and it generates force, right? The force is proportional to the constant and current, right? Meanwhile, this motion inside this one will generate voltage. Voltage will proportional to the motion velocity, right? Then the system you have inductor and capacitor, whatever like that, you have inner resistor, right? Here, most of the case that, let me say that way. This Norton's force, you already get this. This is back in natural motive voltage. So most of this case, okay, here they have inner inductor and inner resistor. Most of the case, the inner inductor is small, L you equal is 0, right? After that, if L equals 0, you can write the current U divided by resistor will be K E times X divided by inner resistor plus load resistor. Okay, now you know the current. You can calculate the force. So the force look like that way, Kf times I, right? So what does it look like that? This force is proportional to the velocity, right? So that's what we call electric damping, right? You have this energy, you have linear transducer here, it generates a force that proportional to the velocity. So this is how energy harvester work, right? Energy harvester is related with damping, that you can take energy out, right? And you have electromagnetic transducer like this one, and you shunt as a resistive load. It acts ideally viscous damping, right? Viscous damping means the damping force is proportional to the velocity, right? This is electric damping. So my question here is how to increase this. Sometimes we want to have another damping, right? Look at this one, how to increase this. You'll say, I will increase B. Yes, you have strong magnetic field, you get more, right? And another thing, you may increase the air, but increase the air, that's trade-off. You increase the length, and you also increase the inner resistance, right? So there are many types of linear electromagnetic transducer, like speaker, right? You break that, and like the voice coil system, you can also design the motor itself, right? Speaker inside is the magnetic field and this voice coil, okay? And vibration shaker is a type of this linear transducer. You can also have electromagnetic rotational transducer. And here, this is ball screw system, right? And ball screw system buoy move up and down, drive this ball screw, then drive this generator, right? You also can have the buoy move up and down, drive the rack pinion, and then drive the generator, right? So, and you can have different transducer, right? From linear system for electric system, and you can put in the system we call the PTO. PTO is more complicated than that, but this gives you sense how to take energy out from the vibration system, electromagnetic transducer, right? Or that can engage different transmission, right? This mechanical transmission, you can have hydraulic or pneumatic transmission. You may have gearbox too. So that's different DC motor, right? This is one DC motor, and this is three-phase DC motor, right? So, and you have different design system, and there's a so-called brush motor and brushless DC motor. Brushless DC motor, you use a Hall effect sensor to control the commuter, right? So this is how it works. And when we design wave energy converter, a lot of time you buy DC motor directly. DC motor, there's some problem. DC motor, the brush after wear, it wear out, right? So in the ocean, it's hard to maintain. And AC motor will be better, right? And another thing is, sometimes people say, okay, how about I buy brushless DC motor? I don't have a brush. It works or not as DC motor, DC generator? I told you, okay, this question is, can brushless DC motor act as a DC generator? No. You say yes? No. What's the difference of motor and generator? Motor changes electric energy into mechanical energy. Generator changes electric energy to mechanical energy, right? For this type of thing, like I show you here, right? And you give current, you can drive the system, right? This become motor. And you have resistor node, this motion can directly drive that is generator. For this type of system, DC motor and DC generator same. Okay, however, for brushless DC motor, when you use a generator, it will become AC generator. You have three phase like that, and you don't use Hall effect sensor to generate that. Therefore, you rotate this shaft in one direction only, one direction. The term you get AC voltage. Okay, so I stop here. As I said, impulse response, I skip that, and I want to show you one figure about impulse response. Okay, so this is free decay, right? And free decay, you put a ball and you give the initial position, the free decay. And this wind turbine, you want to pitch motion, you release that, and you get the type of free decay. This type of free decay, you can calculate the damping ratio, you can get natural frequency, right? So we call the impulse response. Later, when we talk about wave dynamics, you understand why what the relationship of free decay and impulse response. Anyway, and time get end, so we use three more means. Damping, you have right? You have force, you have velocity, right? And you have spring also, you have force, you have displacement, right? And you can have different stiffness, like, right? Especially you have rubber, you can pull that, it becomes stiffer and stiffer, right? And then normally when the vibration, the amplitude is not that large, linear is good approximation, right? And similarly here, this is damping, right? It doesn't mean it's special car damping, right? It's for example, car shock absorber, and one side damping is like that, and then another side is here, and it's not really linear damping. But for the analysis side, we assume this linear damping, we understand the physics, right? And the interesting part is the wave energy side is for energy, wave energy side is totally different. So all this assumption will assume the linear system, right? Small motion. However, for wave energy, we want to have large motion, right? So no matter what, we understand the physics first, and this physics you understand. After we understand the physics, meanwhile we need to know the constraint, the limit, right? So this understanding is based on the linear system, small vibration amplitude, and then if we have large amplitude, you also say, wow, it's different. Okay, I will show you. We are going to see more in the wave dynamics also. Linear wave theory, nonlinear wave. Yeah, thank you. Okay, thank you.